This video is for recap video number 6. I am going to be talking about subfields and differential equations. And Schwartz has 2018 number 6 in a different video. So you'll be able to get that from there. This is Schwartz. So this video should be a little bit more, hopefully less cobwebs have to be dusted off here because we had just gone over this one right before we left, actually. Terminology. So there's a few pieces of terminology here. One is a differential equation, slope field, initial condition, and particular solution. A differential equation, I'm going to do some typing here. A differential equation is one that contains a derivative. So let's just reset the size here. A differential equation contains a derivative. That derivative can be in terms of any variable. So derivative can be in terms of any variable. Sometimes it's an implicit derivative, sometimes it's explicit. Sometimes the derivative is implicitly defined, explicitly defined. Sometimes it's implicitly defined. What that part means is this differential equation has x and y. Sometimes derivatives only have x's or sometimes only y's. Implicit is when we have both variables, x and y. Now, a slope field can be used. So a slope field can be used for a to plot a differential equation. Okay, the way that's possible is I could take little values here, like x equals 1 and y equals 1, and I could plug them in, and I get dy dx when I'm evaluating at 1, 1 is equal to negative 1, because I get negative 1 over 1. So then I go over to 1, 1, and 1, 1 is about right here, and I plot the little slope of negative 1, and I can repeat this for as many coordinate points that I want. The coordinate points don't have to be nice whole numbers. They can be any type of number that you want on the number line, and you'll be able to find the slope at that particular point. And the nice thing is that if you continue this process, I mean, kind of infinitely, like if you continue this process forever, you can end up plotting exactly what a function, the original function, looks like. Now, what I just sketched was not an original function because it was it failed the vertical line test, but this part here is what the original function actually looks like using the slope field. And I'll get to that in a minute. An initial condition, now this one I won't type out. An initial condition is just a point that they're going to give you on a graph, on the slope field graph. So for instance, if I gave you an initial condition of negative 2, 2, it would be about right there. And again, so initial condition is just a point that is on the original function. I'll type that part actually. That's a good one to know. So initial condition is a point on the original function. Given point. Actually, I think I'm just going to make this a different color so it stands out a little bit more. We'll do green. That's a good color. Oh yeah, that's a great color. And we'll just change this to like green. Okay. A particular solution. So a particular solution is going to be something that is a solution that's particular. Olive, weird color. A particular solution is going to be a solution that uses the initial condition to solve for y. Solve for y, always in terms of one variable. Now, when I say in terms of one variable, I mean that there should only be an x on one side of the equation, a y on the other side of the equation, or one variable on one and the other on the other. But it should not be implicitly defined as explicit. A particular solution can also be plotted out. So I'm going to go back to here. So this particular solution is plotted in the sense that not only did we can we get an equation like y equals negative root 25 minus x squared, but we can use this slope field and follow these slopes the way that the slopes kind of want me to follow the slopes. So that would be the initial, that particular solution. In green can be another particular solution at that negative 2, 2, 1, where if I follow these slopes a little bit, to the best of my ability, I get something that looks like that. Again, two semicircles here. And both of these lines that are drawn on the particular, so that these functions that are drawn on the particular, that are drawn on the slope field, ooh, let me try that again. Both of these colored functions that are drawn on the slope field are called particular solutions to the differential equation. Where did my timer? Okay, I found the timer. Steps to solving a differential equation, and I'll type these out as well. And then we'll do some problems, and then I'll say adios. Steps to solving a differential equation. 1. Oh, that color. Change the color quickly. Let's go, yeah, that color. 1. Separate the variables. And Schwartz is going to do this for you in her video. 2. Integrate both sides of equation. Separate the variables, by the way, means x is on one side and y is on the other. Again, they may not be x's or y's, but generally. 3, don't forget plus c. That plus c is called a constant of integration. Step 4. Sorry, I'm just readjusting here. Okay, so step 4 is going to be, I mean, you could do either one. You could solve for y. Solve for y explicitly, or you can I'll just do this. This is the usual one people go. Plug in initial condition to solve for c. So solve for c. Step 5, solve for y. Step 6, check sign of function. Should match y value of initial condition. Okay. 4 and 5 could be interchanged, really. So you don't necessarily have to just plug in solve for y right away. I'm sorry, plug in an initial condition right away. You could solve for y and then plug in the initial condition. You'll get the same answer either way. Okay, so here's some questions that come up with differential equations, and this is over the years that I've seen. They usually come up in FRQs. Sometimes they'll come up in multiple choice questions. And I'll show you a few multiple choice questions that have it, although for you pandemic individuals, you won't have multiple choice questions this year. You'll only have FRQs. But for questions that come up with differential equations, number 1, FRQs, you could sketch a slope field, which again is just plug in points and sketch slopes, little slope segments. Plug in points and sketch slope segments. Okay, let's go a little bit faster here. To match a slope field to differential equation, that's a little bit harder. Usually what I like to look for when I do this is horizontal slopes. Anywhere numerator is equal to 0. I like to look for vertical slopes. Anywhere the numerator is undefined. And then I also look at where are my positive slopes and negative slopes. And I have a multiple choice problem that will kind of utilize that approach. Let's see, find x and y coordinates where dy dx is, okay, so I know what I was going for here. Let me just get a little cursor. C15, here we go. Okay, so find x, y coordinates where dy dx. So where I've seen this come up before is where dy dx is horizontal, where dy dx is vertical, where dy dx is undefined, has a 0 slope. Those are kind of the same thing, but comes up in those different ways. Actually, I think I meant that this line would go there. So that's what I had intended with these two parts. XY coordinates where dy dx is horizontal. If you want to know where the derivative is horizontal, where you have a zero slope, set your numerator equal to 0, and we said that in the one above, and I repeated it 3 times now, which means that it's important. Very equal to 0, and solve. And the vertical undefined, set denominator equals 0. Equal to 0, and solve. To write an equation of a tangent line and use it to approximate, so again, use the differential equation to find slope. Use initial condition to write and slope, so use initial condition and slope. And then based on the information that they give you, they might ask you if this is an over or under approximation. I'm not going to do, I can't do every possible example, so you have to think for yourself how you would do that. It would really relate to use tangent line. It would really relate to this idea where we have 4 curves, and a tangent line can over or under approximate any of these. To find a so sometimes they'll ask you to do a second derivative. Now this one I'm going to put in red because this one is going to be one that could mess you up big time. Second derivative usually will require implicit differentiation. So be careful with that. And then I've seen them ask about concavity, so that means you'll have to plug in the point that they give you, or they may ask you for a max or a min. If at a point you know that dy dx is equal to 0, and the second derivative is positive, you would know that you would have a local min by the second derivative test. And replay that part again if you're not sure what I just said there, and pause it to help you understand what I just said. And then, and again, these are just tough questions that could come up, but are still things that I want you to know. I've also seen them do verifying differential equations. This means that they'll give you the original function, and then they give you the derivative, and you have to take the derivative of the original function. And check that it matches their derivative. Finally, there's proportionality, and I'll do a problem with proportionality in a minute. And finding the particular solution is already what I just gave you. You have to use those six steps to solving a differential equation. I'm putting this part in quotes here because the phrasing never changes. They may ask you to find domain and range. Those domain and range problems are usually 1 point. So they rely heavily on your pre-calculus stuff, which I am not going to go over in this video. Domain and range, it's pre-calc. And usually just 1 point is what I said. Okay. I'm going to stop the video here, and I'm going to go over these problems with you in the next video.